Okay, here's a clear-cut method of proving that there is no such thing as centrifugal force. But before I start, I'm going to say that S over R equals theta for a circle. So if you have a circle, what that means is if you have a circle like this, uh, let's do that. Let's erase this. Okay, that looks good right there. Okay, so if you have a circle like this and a spatule arc like this, theta. Let me make this look nice and neat for you here. You have a spatule arc length like this and a scalar length. Okay, the scalar length. Okay, in other words, you have a vector r. Well, the magnitude of r defined is just equal to some length r. So the magnitude of this vector is equal to some length r, right? So now what I'm going to do is I'm going to say S equals r times theta, and ds dt equals r times d theta dt. So, but this d theta dt is usually represented as an omega, so we're going to have, and this is going to be v, so what we're going to have is v equals r times omega. Okay, like that, make it nice and neat. Okay, now I want to drop a perpendicular. In geometry, we always had a rule. If all else fails, drop perpendiculars. Okay? Drop perpendiculars and solve. Okay? So, by definition, r cosine theta equals x and r sine theta equals y. By definition, r cosine theta equals x and r sine theta equals y. Okay? Now, check this out. A linear displacement, S, would be a linear displacement is velocity times time. Okay. Angular displacement, theta, equals omega times the time. So so wherever you see a theta, you can substitute this omega times time. Okay. Now we're going to use what is called a vector to represent this. Okay. So call this vector r of t equals the scalar r cosine xi plus the scalar r sine, sorry, that's not x, that's theta. Okay, that would represent x. So r cosine theta equals x, r sine theta equals y, like that. Okay, clear cut, right? See where I'm getting at? I'm saying xi is x distance times this I vector, which has you define I as a unit vector with magnitude 1, and then yj. So if you want to find that magnitude, you would say x squared plus y squared, and you take the square root by Pythagorean's theorem, and you get r, right? Well, that's what this is based upon. Okay, that's simple. It's not all that hard. Okay, so now I'm going to replace this theta with this omega t. So I'm going to have r of t equals r cosine omega t I plus r sine omega t j. This is really going to be clean cut here. You know, I mean, clean cut, clear cut, and very, very explicit. Okay. So this is a vector, and this is the scalar r. In other words, the distance from the center to a point on the circumference of the circle. This point here with a tangential component of velocity going this way. Okay. And because that's a vector, it points in that direction. Okay, now what I'm going to do is I'm going to take the first derivative. I'm going to say dr, derivative of the vector, with respect to time, means I'm going to have to take the derivative of both of these, okay, with the scalars. Scalar is a constant, but omega is what's changing, the angular velocity. So now I'm going to have r omega sine omega t, and that's going to be negative. And when you take the derivative, because the derivative of cosine omega t would be negative sine omega t, rw sine omega t. Okay, so, and then I take the derivative of the sine, I still have a plus right here. So now when I take the derivative here, I get rw sine, cosine, sorry, rather. The derivative of sine is cosine, of course. Omega t, j, like that. Now I'm going to take the magnitude, remember Pythagorean's theorem, the magnitude of dr dt, the magnitude of dr dt, and I'll just write it out for you to show you exactly what I'm doing here. So I'm going to take this r omega, okay, this is going to be a minus, but I'll do it this way. Okay, I'm going to take the r omega out, r omega times this negative sine omega t, that quantity squared. Remember, it's not going to matter if it's positive or negative, because when you square it, it becomes positive again. Plus this cosine, excuse me, omega t, quantity squared. Okay, so now when I solve this, I get the magnitude of dr dt, the vector dr dt, equals this, when I square this, okay, I have to square this also, because I took it out. So now, when I square that and take the square root, I'm going to get r omega times the square root of sine squared omega t plus cosine squared omega t. I mean, if you wanted to put the I, and j in there, you know that the magnitude of the I vector, not imaginary numbers now, the magnitude of the I vector is just going to be 1. Okay? The magnitude of the I vector is 1. That's how, by definition, the magnitude of the j vector, is 1. So I can just take that out right there. It's like factoring out a 1, which just gives you everything in there. Okay, so now I'm going to have this v equal to the magnitude of dr vector, dt vector, and that's going to equal to r times omega. Now, if you remember from trigonometry, sine squared theta plus cosine squared theta equals 1. So that's just going to be 1. So you're going to have 1 times r omega. So what it's going to give you? It's going to give you v equals r times omega, like that. Or you could reverse and say v equals omega r, like that. So I just proved that. Okay, so the magnitude of the tangential velocity vector is just going to be omega r. Okay, so this is the magnitude of the tangential vector, tangential velocity vector. Excuse me, and that's going to give you the scalar value of the speed, which is r times omega, or omega times r. Okay. Now, for the acceleration. Okay. Keeping in mind that I calculated that the magnitude of the velocity vector equals omega r, right? So I'm going to rewrite my equation again. I'm going to write, we found that dr, the vector, dr dt, is equal to negative r omega sine omega t I plus cosine, r omega cosine omega t j. We found that. So if we take another derivative, the second derivative of this vector here, if we take the second derivative of this position vector here, let's call it position vector, we take the second derivative of that position vector, which is the second derivative of the tangential component of the velocity vector, we are going to get, well, take the derivative of the sine, you're going to get cosine, you take an omega out. So now we're going to have r omega squared, still minus here, cosine omega t, I, minus r omega squared sine omega t j. Now I'm going to take the magnitude of that. So the magnitude of that, which is the acceleration, by the way. Sorry. Okay. So the magnitude of this dr dt is going to give you in the square root thing here, in the radical symbol, you will have this quantity negative r omega squared, that quantity squared, because you can factor it out, plus, not plus, times, sorry, times cosine squared omega t plus sine squared omega t. And that's all under the radical. This cosine squared omega t plus sine squared omega t will go to 1. Okay, and that'll be r squared omega to the 4th. So you're going to get the second derivative of this position vector with respect to time, the magnitude of that, equals this square root of r squared omega to the 4th, which is going to equal to r times omega squared, right? But what did we have for, we said v equals r times omega, right? So if v equals r times omega, v equals r times omega, then in terms of omega, we got omega equals v over r, correct? Okay, so now we're going to have r times this v over r quantity squared equal to this acceleration. That's going to be the magnitude of the acceleration vector. I'll write it like that. The magnitude of the acceleration vector will equal to r times v squared over r squared. So the magnitude of the acceleration vector equals r times v squared over r squared. And that is going to turn out to be v squared over r. So what are you going to have? Okay, so you're going to have, just write a simple a there with nothing over it. That's just the scalar value of the acceleration, the scalar value of the acceleration. And by the way, the acceleration would be inward toward the center. So it's v squared over r. That's the acceleration that is holding the point on the surface to that surface. It could be a car going around a curve. It could be a car going, say if you have a car that's really traveling around a curve very, very quickly. Okay. So what are you going to have? You're going to have force centripetal. Force centripetal equals the mass times v squared over r. Okay, so that's the scalar component of the force centripetal. Okay, so what does that prove? Oh, that definitely proves that if you go around that curve, it definitely proves that your inward pull, the inward pull, is not going to be due to there's nothing going to be pushing out from the center of the circle. You're going to have an inward pull of the circle. So that proves right there that there's no such thing as centrifugal force, because when you're talking about a point on the surface of the circle, right here, okay, there's going to be a force, an acceleration, okay, that goes in toward the circle, okay? And if you were going around that curve and you went too fast, what's going to happen? If you're going around and you're round and around and you go too fast, you're going to go straight like that. There's no force that's going to push you that way. If you got on a motorcycle and you went around and around and around in a circle like this, and you went too fast right here, if you overcame the frictional force right here, then you would go this way. You would not fly this way. You would go this way. And say if there's a wall like this around here, what's going to happen? You would fly straight into the wall this way. Okay? So people need to get that out of their head, that there's a such thing as centrifugal force. There's no such thing as centrifugal force. There is a such thing as centripetal force. Centripetal force. There's a such thing. Exists. Okay. So centripetal force exists. That's true. Okay. But centrifugal force does not exist. No such thing. There is no such thing as centrifugal force. And centrifugal, the word comes from centrifugal. Centrium meaning center, and fugal meaning fleeing. There is no such thing as a center fleeing force. Okay? There's just no such thing. I just proved mathematically that the centrifugal force is just a fictitious force. But in the old days, before mathematicians really came along and investigated these things, before physicists who knew mathematics came along and investigated these things, it was believed that there was a force that comes from the center and emanates out. But that's not true. That's been disproved with mathematics. And also through many, many experimentations, the math disproves it, and the experimentations disproves it. So what we're talking about here is we're saying that centripetal force exists, centripetal force, an inner force that seeks toward the center. Now, you have a frictional force that is holding, if you had a motorcycle here, there's a frictional force that's also holding it to the road, okay? So, if the frictional force, you can find the maximum velocity that you can go before you fly off that road by solving for the frictional force. You set the frictional force equal to centripetal force, and you solve for v, and that will be Vmax, okay? And then you can use that formula to determine if a velocity is greater than what you discover using that formula, then you will fly off the road. If you go past that velocity, that's how the civil engineers determine the maximum speed that you can go when you're going around a curve. So this is really just vector analysis, and it's also related to civil engineering, and is how everything works. So I just proved mathematically, unequivocally, that there is no such thing, absolutely no such thing, as a centrifugal force. No such thing. So get this reference frame stuff out of your head, and understand that only centripetal force exists, because only centripetal force can be represented mathematically. It only makes sense mathematically. There's no equation for centrifugal force. There's no equation for centrifugal force, but there is an equation for centripetal force. So just understand that true, centripetal force exists. Centrifugal force does not exist. No such thing. Okay. Okay, so thank you for watching my video, and I'm glad I could help.